we'll have another speaker, which is again a graduate from my group, Dr. Sahil Rohila. So we'll be dealing with two different aspects with high entropy alloy. First, I will talk about basics and high entropy alloy, where he will be carry forward some alloy design and phase evolution typically used or required to understand the high entropy alloy. And he will also do some online simulation to demonstrate how alloy design and phase evolution can be understood using some tool like thermocell and all. So with that, anyway, once I will come to that, I will briefly explain, then he will carry forward. So let's start with the first work, which is high entropy, which is basically in a basically electrospark deposition. So give me a minute. I'll need to share my screen, and then please feel free to interrupt me whenever you want. I have any clarification on that. Okay, so I'll just share my screen, and I hope my voice is audible, and I hope my screen will be also visible. Okay. Okay, I guess my screen is visible now. Okay. So first talk is going to be on electrospark deposition, a novel method for improving the surface properties of alloys and steels. Okay. So before I go for I request others who are not speaking can mute their audio so that noise can be reduced.
Almost all the people's voice are muted, sir.
Okay, fine. No, I see some background noise is coming. Okay, so let's start with. So before I start, many of the work is actually carried out no longer by me. It's my group or a group of students who does the work. Okay. So before I go on, let me first acknowledge some of the students who are basically the PhD as well as MTech students, where we have contributed significantly in this area. We start with Dr. Rahul Mane, then we have Dr. Sahil, then we have Subhendu Nashkar, Raj Shekhar, Prini Sharma, Chandrakant, and Sriman. These are the students who have largely contributed in this particular talk which I am going to. Some of their work will also be included here also. So, okay. So with that, let's go back to our business. So electrospark deposition. I'm sure many of you will be aware of some of these techniques. It can be used for surface properties improvement in variety of materials, basically metals and alloys. Okay, so let's talk about this. It's basically a electrospark. What is electrospark means? Whenever you bring two electrodes together, you see there is always a electrical spark, right? So this very same technique is used what we have so-called arc melting furnace or many of such things. So whenever you control a proper voltage and current, you can actually control the temperature generated between this plasma or arc. So this region is nothing but what we have here, what I can call this one as this is the arc. Electrical arc is generated where huge temperature is generated, and temperature is so high that one of the electrode which is there is a possibility temperature can so high that melting point of this melting point of this electrode can be so low, or temperature of this arc is so high that the electrode can actually melt, and when it is melt, it actually end up depositing. So this is the very basic techniques. So okay, and such you can see here some of the examples here. You can see this is here you can see this is the workpiece, a substrate, where this is the layer. What we can see here is a deposited layer where this is your electrode material, where material you are actually going to deposit. So there, whenever this electrode, two electrodes, one is the substrate, one is filament, which is basically you are going to deposit the coating material. When it comes together, there is going to be huge electrical spark, and temperature of spark is so high that one of the electrode can actually melt. And there the temperature and other things can be controlled. As you know, these are electrical dependent parameters. So that simple method is used for making a layer. This simple method has led to a lot of advantage. You can do variety of things. We will discuss as we go on. And some of the work, so this basically this talk will consist of some of the work reported in the literature, just to brief you. And then few works which has been carried out in our group, will also try to show some of those works. Okay. As I said, electrospark deposition are also referred as electrospark coating. So it is also referred as a electrospark coating. Okay, so this ES, the electrospark, so deposition is also referred as a coating in many sense. So you will have to work electrospark deposition or electrospark coating. So it is very commonly used. So basically nothing but micro arc welding, you can call it. It's similar to the process what you know. Material deposited in a molten form during the spark, as I explained. It can have various advantages. It can do several things. It depends on the end user, how you want to use it. It is a very good process for depositing a wear resistant and corrosion resistant coating. Also, you can also, in addition to the having a fresh coating, you can also use for repair purposes, for example, to improve the performance, to repair. And of course, if you are thinking that component getting older, you can some surface treatment that life of the component can be enhanced. This is just a table. Sorry for messing. I have asked my student to prepare the slide, so he has put the way he do for PhD. So what I want to say, there are a variety of, you can see in the top, wear resistant coating, then there are corrosion resistant coating. There are a lot of things which used for surface modification. And these are some of the basic coatings, materials like hard carbides. You all know that most of the wear resistant coatings are made of hard carbides. Like when we talk about hard carbides, this typically comes from tungsten, tantalum, hafnium, molybdenum kind of group, you all know. And then we have a lot of steels, tribolites, and of course we have some of the borides, which is also known for a coating material. There are a lot of corrosion resistant steels, corrosion resistant coating on steels, inconels. So you can also deposit the aluminides. There's a variety of medium and high entropy alloys, and these particular things you can use coating in, let's say, for example, super alloys and all that you can do it. A lot of other, you can see such variety of entropy and many novel improving of many of the other materials. So it can be used for a variety of application. This is the equipment which you have. Basically what you see below is our electrode. Is a very small electrode deposition unit. And what I want, you can see here, you can hold the, you can see here, this is holder sample is fitted here, and this is just hand holding things, and you can do the deposition coating. So this is what you can see here. So this is the electrode which will be rotating continuously, and you can fix your substrate here, which is actually connected with electrically here, and electrically this one is connected, and you can actually do the deposition. So as I mentioned, actually if you look at we have a substrate. So this is the substrate or workpiece you can call it, and if you want to deposit the material, this is your material which is rotating continuously, so that you can have uniform coordinate. And whenever this electrode, which is your material, touches with the your test workpiece, you will see that huge spark is being generated here, and the temperature, as I mentioned, you can also refer as a plasma arc or simple electrical arc. But that important point here is whenever a temperature of this arc is going to be so high, it can actually melt your depositing electrode, and whenever it is melting, it forms small droplets and these droplets actually go and deposit here. Okay, so this is a very simple technique, not a big science here, but it's very effective method to do that. These are just a splash of a drop. You can see here between you can see just a splashing. It shows that how the metal has converted in a liquid, and you can see that how a splash has been created. There are a lot of process variable, as I said. There are a lot of electrical related, since it is an electro spark, means a lot of electrical related parameters come into play related to the power supply, resistance of the material, voltage, current, which is basically so many other things we need not to, frequency, so many parameters you can play with, as you know, like all other techniques. There are a lot of physical things are there, which is basically like how your surface is prepared, what is the environment you surface is prepared in the sense like material, it is rough surface, or let's say you are depositing a material here, right? So whenever you're depositing a material, actual material may be too much of like rougher surface. So what happened? You can prepare the surface is smooth. So these are the physical things you can do it. And whenever you are depositing, then there is also a atmosphere come into play. What we call is environment. Environment is, if you are doing in open air, it is fine for some material, but some of the material which is reactive in the air, for example, maybe possibly you have tendency to form the oxides, for example, right? So you can also use it in where. So this can be done in an open air. It can be done using some inert gas. So if you do not want, then you can use an inert gas around that. You can actually do also in a vacuum. So there is a possibility depending on what kind of pair you have, pair in the sense substrate and you are depositing material. Depending on these two pair, how is their chemical natures are there, you can actually choose the atmosphere accordingly to avoid unnecessary oxidation also. So this can be, so you can call it, the process can be conducted in an open air as well as controlled atmosphere. Okay, so there are several parameters which affects. Here, if you look at the typical spark life, is just a few milliseconds, very few milliseconds. It's a rapid material transfer technique and self-quenching. Self-quenching in the sense, since it is going to be a huge substrate and small droplets are coming, it's immediately, because of conductivity of your substrate, this actually gets quenched, solidifies instantly without really having. So it will also have a very small conventional, compared to conventional welding process, it will have extremely small heat affected zone. And obviously, since it has a very small heat affected zone, it also have but very minimum defects at the joint. So you will not see much defect in the material. You can see this, some of the samples of aluminum, for example. This aluminum sample is basically, if you look at this portion, is actually the electrode deposited. This is the layer which is deposited. This is those who are familiar with metals and alloys. If you look under the microscope after polishing, it looks like that. And when you etch it, you can clearly see after etching, this layer of microstructure built up in a new layer can be clearly distinguished. And this is the interface here. You can see here. And interface is so smooth here. Okay, so it has several advantages. Let's see what other things can be done. If you look at the microstructure, since I come from metallurgical background, where everything we try to correlate in terms of microstructure, what kind of microstructure is there, what kind of phases are there, and we try to correlate the material performance through this. So we have by default tendency to look at the microstructure and understand their behavior. And when you look at the microstructure, what I am trying to say is, in this technique, the substrate structure are hardly changes. We do not do major microstructure modification. The process does not affect much to your substrate. So substrate remain as it is without really altering it. Okay. And also whenever we coat, I will show the microstructure, the whatever new layer which you build, this new layer, whatever new layer you build will have very fine microstructure. I hope you understand microstructure means I am talking about fine grain size like this. Okay, finer the grain size, better the property, you already know. There, depending on the coating parameter, actually, this is the larger one, what students are doing here, because we are interested on large thickness. You can actually do a very fine coated layer. Thickness of the coating layer can be absolutely very few, just a micron to, you can even build up the layer to few if you want to have much thicker layer. So there is a possibility in this process that you can build up the layer depending on your requirement, what is your in application. There is simple comparison between a detonation gun coating, basically, which is again different types of coating, you may be aware, with electro spark deposition or coating. You can see there, here the wear performance has been given for two techniques. Y-axis is the wear one, you can see here, okay, and this is the contact stress. You can see there, in case of electro spark process, the wear is extremely low, where compared to other techniques which has been used are very high. This is another comparison of two types of bend test. So I hope you are familiar with the bend test. What you do in the bend test is, you have a material, let's say, okay, I am depositing. Now, to understand the performance of a coating, what you can do is, you can do it a bend at the center. Okay, so what you are doing here is, this one you are bending at the center. Now you have a coating. Okay, and you know that the coating material property and the base material property are different. There is a possibility, let's say this is for some steel or so. If this is your steel, let's say your substrate is a steel, I'm telling example, and you have coated some hard material on that, then you will see that the steel modulus is different, coating modulus is different. Their modulus or Young modulus are not the same. Similarly, their ductility are also not the same for your substrate and your coating. Let's say substrate we call it a S, coating we call it a C. Then you will see that their modulus is not same. Also their ductility is also not the same. And when you are bending, what will happen? This portion is going to be a huge tensile stress. So huge tensile stress will build. If ductility is not so good, there is a possibility that material can actually start failing here during the bend test, right? So if you see, there is one example here has been given. There is a rod which was straight earlier, okay, and then it was coated here, two different methods, and after that it is bent. And when you bend that, you can see here the peeling of the coating material. Here what you are seeing here is essentially because of the coatings are brittle in the nature, not as ductile as your substrate, and you actually see that things are peeling out here. This is a normal degun coating, where you can see that electro spark deposition, there is the coatings are actually much, the deposition, the delamination of coating, what you see is very minimum. After bending also, you will see coating stress. The reason, the difference between these two is basically it actually creates extremely strong and very good metallurgical bond without having any defects. So you can see here the performance of two coatings are completely different compared to when you are comparing to other methods. These are some of the work carried out in our group. For example, is a MTech student who carried out his work initially long back, almost 3 years back. So as I mentioned here, this is a substrate which is made of a steel, and this is a simple sketch I can show. This is your electrode, which is basically what we are doing here is we are trying to use high entropy alloy as a coating material in a steel, on the steel substrate, and the steel here is 410 martensitic steel. So what you do is we have made a filament, fine filament through the powder metallurgy sinter technique, and this filament is used actually for to avoid the oxidation. You can also have a shielding, you can have a gas flow, so that we use a argon gas, so that the spark and around is covered by the gas, so that no additional contact with the outsider air, so that any oxidation formation also can be avoided. Okay, so this is the electrode discharge coating. Let me show some interesting result. What he has shown here is that very first thing is start with our XRD. If you look at the XRD of the substrate remain the same, whatever still we have. However, this what we do here is, let me brief what I'm trying to say is, material is prepared through the powder metallurgy techniques, the filament. We call it filament. This filament for deposition, electrode, we call it a filament, is prepared through the powder metallurgy technique. Okay, this powder metallurgy techniques, which you go for a sintering, and this sinter sample is machined to make the fine filament. Okay, and this filament is actually now used for deposition. So there is a sintered body, and then there is a deposited layer. Now the X-ray, what I am trying to show here is the comparison of phase evolution on a sintered condition. Here I am taking a X-ray, and then after deposition I am taking the X-ray. Okay, and where it still remain the same. So this two is basically one at the sintered state, and same material after deposition. We see that during deposition, is there any change in the microstructure or not? You will see that phases are nearly the same. In fact, the sintered sample, if you look at those who are familiar with the phases, it is a basically BCC rich Li. This particular Li is BCC phase rich Li, which having a small fraction of FCC phase. But along with that, you will also, the S sample material will have some other unwanted phases called B2 and sigma phases. But when this material is getting deposited, this peaks belongs to B2, the sigma phases are actually vanished, and you have more uniform microstructure consist of mainly BCC and FCC phases. So you can see that the phases are absolutely smooth and have more uniform. Unwanted phases are no longer there. So you can see that deposition can give a much desired microstructure compared to even S-sintered material. If you look at the coating, you can see that this is the substrate side. This is the microstructure of cross section. Cross section in the sense, let me explain what I am trying to show here. You have a substrate, and here in this substrate, you are building a layer here. Okay, so we are building the layer here. So this layer is being built up. So what happened? We are building a layer here. So what you have here is the small layer is being built up between this. Now this microstructure, what I am trying to show, that this side of face, the cross section, this is the interface. This is the interface. What I have shown here is an interface. This is a substrate, and the upper portion is actually the coating side. So we are looking at the cross section. We are looking from this side, the cross section microstructure. And when you look at the cross section, what you have here is, you can see that perfectly smooth cross section, no defects, nothing. You can see the interface very clearly. So this is the basically your interface. Okay, so this what you see here is the interface. This is the coating side, and we went in a little bit more because we are interested to see a little bit more in microstructure evolution. When you have a more magnified in under ACM, you can see different microstructure. Very low magnification, you do not see much, but the moment you zoom in, you will see there a lot of microstructure features are start appearing. Even very small pores are visible in some places, which is expected. This is not unexpected. In addition, we can also see that very diffuse layer. The actual interface is extremely smooth. In a deposited layer, there is a possibility having a few very small size of less than half micron, 200 nanometer, 300 nanometer pores are available few places, but otherwise you will see mostly unison. We have also seen that the microstructure, if you see, you have two different types of microstructure built. The microstructure very close to the surface has a coarser microstructure, and away from the interface you see the finer micro. So what it means is that you are depositing a coating layer here, and we have, this is the coating layer. Okay, so this is your substrate, this is a coating. Now what we are doing here, we are looking at this interface, and you are looking very close to the interface microstructure. Another, we are trying to see little away from the microstructure. Okay, and you will see that when you are moving from the interface, probably their microstructure, and this is probably because of the heat. whenever we are building a layer by layer, the past layer will always goes for multiple heat treatment. It's just like you are additive manufacturing. Layer go multiple heat treatment or annealing effect or heat treatment effect. So that leads to a fine coarsening of the inner layer compared to top layer, because it has huge thermal cycling. It is going, this layer is going under huge thermal cycling, because layer and layer is you are building, right, gradually after several rounds. So this, because of having a several thermal cycling, it leads to a slight gain coarsening compared to the layer which has seen the less number of thermal cycling. So there is a slight change in a microstructure you can observe if you look under the microscope. So here the substrate is a steel and the coating is a high entropy Li, aluminum containing high entropy Li. We are more interested a little bit more on diffusion profile. As I told you, we understand out of 5 elements how those elements are actually. So this is the elemental mapping in the SEM, and I'm sure that many of you are knowing that how compositional analysis are done in SEM, where you can actually map which element is where. So you can see at the interface and at the zoom section of this, whatever we have seen, white line has been mapped. So this is the interface. So we can see one by one. So this is for the chromium. So this Li particular contains aluminum. So aluminum, cobalt, chromium, iron, and nickel. These are the 5 element system. Okay. So because this has a 5 element system, each element is basically mapped. You can see here the chromium, because it still also contains a chromium. So you can see chromium is there everywhere because this base is still also chromium. And since it is the steel, then you will also see the iron. So this region you can see the substrate, which is basically steel, means is iron one, and this still contains huge amount of chromium. So you always see the chromium is almost both sides there. However, 2 of the element, 3 of the other element you see significant change, because chromium and iron is already there in a base element. Is very difficult to differentiate them. However, you can see in iron measurement, you can see very clearly, since it is a pure steel, pure iron having a majority of the steel, so you can see their color is much brighter, means you can see the density of iron are more compared to your this side. If you look at the cobalt, you can see this region contains high density of cobalt compared to where pixel, you can see it become very low. Similarly, nickel, you can see here the coating, this clearly visible. This side is nickel region, and gradually what you see that concentration of nickel is gradually decreasing. Here also you can see cobalt concentration at the interface. When you are moving, basically the concentration is start decreasing. Near the interface it is higher and the concentration is gradually decreasing. You can see here, similarly, aluminum rich means it's the coating has high aluminum rich. You can see the location of chromium, but the moment you go in the inside, you will see that these are the diffusion zone where you can see the concentration of aluminum decreases. So if you try to plot a curve as the interface, this is a coating and this is a substrate, you will see at the coating, the element of aluminum, nickel, and cobalt is going to be very high. And the moment you go at interface, their concentration gradually decreases. And you can see that this. So it shows that, and moreover, what important thing is we do not see any kind of segregation. We do not see any kind of precipitate formation. So no segregation, no precipitate or intermetallic phase one. That means that the whatever diffusion you see is a purely and very nicely homogeneously diffused in the base material. So it says that very nice and uniform Li formation at the interface, which is very difficult to get in a normal other coating. Okay. And if you look at the profile, their hardness profile, now you can see the cross-section hardness profile. And when you look at the cross-section hardness profile, this is a simple microstructure. This is the base material side, substrate side, which has a lower hardness, means when you do the indentation, this is a Vickers hardness. I am sure many, I hope you all are aware of what is Vickers indentation. When you try to make Vickers indentation, when material is lower hardness, you will make a big indent. But when you go towards the coating, you will see that indent side is started decreasing and decreasing. That indicates that this side has, the coating side has a very high hardness. And gradually when you go towards interface, so these are the region where you see a sharp drop in the hardness. So this is actually your interface region, or we can call it diffusion zone. And then When all the diffusion zone is over, you have a base material. You can see which has a lower hardness. You can see clear change in a 3 different regions. Region 1 is a coating region. Region 2, you will see the interface region, and you will see the base region. In a region 1 also, you can see there is a change in the, as I mentioned, change in, it is not a straight line. It is not a straight line. You can see there is a slight slope on that, right? So this can be understood by the, as I showed the microstructure, at the, because of this region has very slightly large microstructure compared to top region where it has much finer microstructure. I have shown the microstructure earlier, coarse microstructure and fine. Coarse microstructure means lower the hardness, finer the microstructure means higher the hardness. Okay, so what I was mentioning here is, you can see here coarse microstructure and here fine microstructure and coarse microstructure. So you can see that how the profiles are changing. Okay, so this is their hardness, and hardness can be actually improved significantly, somewhere from 250 below 300. This the base material has gone all the way to 900. So there is almost 3 to 4 times jump in the hardness value, and with having a very good metallurgical bond. Okay, so this is the very good characteristics, and which is extremely tells the how useful the method is. We have also done the evolution you can do with the wear performance. If you want to have the good hardness and wear properties to be studied. So what we have here is, we have done we made a pin of steel, and this pin of steel is actually coated with high entropy alloy. And after that, we do the standard pin on disc, which you are familiar with, where the disc is your typical EN steel reference disc, and this is the rotated. And when you see their profile, you can see there a material which is uncoated pin, and this y-axis shows the wear rate. It shows a huge wear. But when you have a coating, you see that there is a wear has almost dropped. It says that this whatever coating you have done has a very good wear resistance. There is a significant drop in the wear behavior. If you want to look at their friction, the edge steel has a higher friction coefficient. Coated material is expected to higher friction coefficient because of high entropy alloy, where the substrate is having a lower friction. So this is in line with the material behavior. This is the microstructure. This is the edge steel without a coating, and after coating you can see the layer which has broken from the high entropy alloy layer. You can see that the layer. So this causes a little more friction. However, it has a more wear resistance. Okay. There are a few more case studies carried out by our group, which is tungsten carbide coating on steel 316. You can see this is a substrate, and the left side is actually the coating, where right side is a substrate. And if you look at the properties, this is a substrate without coating, and after coating you see the huge jump in the hardness. So this is the hardness of the coated sample and uncoated sample compare. So you can see the substrate, and there is huge jump in the surface hardness after coating the material. As I said, similar thing microstructure you can see here also from the surface. So this side is your coating, this is your interface, and this one is your, so you can call it region 1, you have a region 2, and you have a region 3. So you can see there in a substrate has this much, and the substrate hardness has actually increased drastically by having the coating. And you can see the same thing in your file. You can see here in the photo of your indents, you can have large indent, and the moment you are going towards the coating, you can see that finer. In other words, in the coating side, you see the finer and finer indent size. The moment you are going towards base of the material, the indent size is gradually increasing. That indicates the hardness. Okay, where this one is your top layer. So you can analyze your samples, how a gradient hardness is happening, and it's extremely interesting to see such results. Similarly, as I showed here also, you can see that after coating, this wear performance, you can have this much of wear rate, where material has this much of material loss has reduced significantly here. You can see the difference between the two curve. There is a without coated material, and after coating, you can significantly drop in their wear behavior. Red line is the coated sample. This is some example, and you can actually find variety of application for this one. This is some example, restore thin walled component, where you can see. So one of the application can also be a repairing purposes of the surface defects, mostly which are finer in the nature. You can see this component, you can see there the indents are made. Basically, these are damage, permanent deformation and defects are there. And this can easily be, you can see here, you can make this with a electrospark deposition and followed by polishing, you can actually restore the surfaces. So here you can see surfaces had been restored. You can see the turbine blades, for example, there are defects has been generated and this damage has been actually. So you can do the selective repair, and then once you polish after selection, you will actually see your defect is fully repaired and material can be restored for application. So this increases the service life of your component significantly. So this method has extremely useful, lot of variety of application in several purposes. You can do in a industrial level, for example, repairing of several things, primarily metal industries, like we need a lot of tools and dies and other things, which is always subjected to the surface damage. And those surface damage can always be like forming presses and dies. Every time you have a small defect, you can repair it. So once you can repair it, basically life of the component can become. So this is just, you can actually do the coating at the surfaces or coating in the wherever required. And similarly, these are just the application. Of course, these photos are not very clear since it is large scale. You can actually the hard coating in the tooling, the surface side, which is going to do the actual here. These are the layer. You can do the coatings. Okay. These are other example of, let's say, repairing of the golf course. For example, you can see here the golf course club has been actually damaged here. It was actually fully restored by electrospark deposition. The beauty of this is it doesn't damage other part of the material. It's a very selective, created in a small zone, so it doesn't affect much larger part of the component. You can do, this is another example, you can damage, repair can be done even for the selective locations. This is another example, as was mentioned about turbine blade repair. Of course, this is a generic photo, but what I wanted to say here, as I mentioned earlier, you can have repair and restore actually the damaged area after polishing. It can actually be sustained. Means the component can further continue to service to some more year rather than retiring it or throwing it back. There is a slight difference. The process is similar to the welding. However, in a conventional welding, you see the major problem is huge amount of heat affected zone, which essentially damages the base material. Here, we will see very small input and very small low heat affected zone. It doesn't damage your base material. So material without compromising the properties, it continue in the service. This is one example where what it is that you have this is the for example, this is for superalloys. This is a substrate. What you can see here is a substrate, and this is the deposited layer. Okay, as deposited, when you measure the hardness, as I mentioned, the hardness is higher. However, in the substrate, you will see is the hardness is lower. And many of you will be knowing that superalloys are subjected to heat treatment. And whenever you do the heat treatment, there is something called the gamma prime and gamma double prime. Those phases start precipitating over long aging treatment. So this deposited sample has sent for the long aging treatment. And during aging treatment, you will see that both the heat affected, basically the base material as well as your coating essentially comes out in the similar hardness range. So your material which has initially had, let's say, in a heat affected zone, these are the heat affected zone where you have damage where hardness are higher because of control of kinetics of the gamma double prime, you will see that hardness is actually restored. So now coating as well substrate had nearly the same hardness. So what happened? Your material can continue performing in their services. These are some similar examples. Just look it. So there is a, that I just want to touch a very small section related to additive manufacturing. The additive manufacturing available in various ways, direct deposition as well as powder. What you will notice here is there many times, if your parameters are not proper, or your powders are not proper, or flow rate of your powder is not proper, there is a possibility of having a surface imperfection. So those residual surface imperfection can be actually be repaired using the, you can see some other example here. This is the surface. If you look under the microscope, there is a possibility that you will have lot of surface roughness is created under the microscope. However, this surface damage, whatever a minor amount, and you can see the microstructure. You forget about what is written here. You see the microstructure. If you do this, this is the base microstructure, and over that, this new microstructure has been built up over the deposit. So it can actually damages wherever the surface damages are there. Huge amount of carbide materials are there, which can be used, as I mentioned earlier, for wear resistance, hardness, corrosion resistance, etc. In a summary, let me summarize the work. Electrospark deposition is a pulse arc micro welding process. It creates very nice metallurgical bond with low input, and then electrospark exceptional wear and damage resistance can be used and modify the surface. What we are doing in our group, I just quickly want to take 1 minute to brief what else we are going in this area, so that if anybody is interested can actually start doing it. So what I want to mention here is we do the coating. Okay, so first we do the coating. Coating. In a coating is, as I mentioned, we do surface, then we related to the hardness measurement. We do the wear resistance, wear studies. Okay, a lot of wear tests. These are the standard. Apart from that, we look at some metallurgical aspect. We look at is the phase evolution, microstructure evolution, and if there is another microstructure feature, any other microstructure feature like orientation, textures, etc. Okay, these are the standard work which we are looking at. There another side of work which we have initiated here is damage repair. So damage repair is essentially, you can think of a component, okay, assume that this component is damaged. What you do is you do the electrode deposition, restore the surface, and polish it, so that after polishing you have a smooth flat sample, right? And this flat sample is being tested for a tensile test or compressive test or bend test. And you will see that with compared to the base material, you take some base material with similar strength. So you do the 3 different types of tests. 3 tests you need to conduct. One, the base material without defect. Okay, the material which you artificially create a defect, and then sample which has a defect repaired. Okay, I'm just telling an example here. This tells you whether after repairing how much, if you're testing the base material without any standard, you make sample as per the standard, and you see whether property, whatever property you are getting or not. Then damage sample section, or you can create artificial notch, V notch or so, and you test. You see there is a drop in the strength because of damage, and you heal it, and again test. You see that strength is restored to base material or not. So these are kind of work which we are interested to work out. Some of the students are involved in these 2 types of work, where base materials we are taking as steel. There are variety of steels are there. we have titanium alloys. We also work in Inconel, basically super alloys based. So 3 different types of substrate we are using with different alloys, of course, not 3. And high entropy alloy coatings, tungsten carbide coating, and such some more coatings we are trying. So huge work is going on in our group in this material, and we find that results are very interesting. So it can be used not only for coating, it can actually use for a selective defect repair in the surface. Of course, the defect is not deep, mostly in the surface of few mm or few micrometer, so that cracks or whatever defects are there should not propagate, but it can be healed in a time before it start propagating. Okay, so this is all about electrospark deposition. I will be happy to take a question if anybody has. Thank you very much. So I give some times to, if you can have some question, please feel free, so that I can spend some time in interaction and clarification of your doubts.
Any participants are interested can post a question to the sir.
I will not be able to see the your post because it is you can directly talk. Please
Okay,
talk
you can
directly.
directly talk it.
Because I will print full screen, I can't see what is posted there.
Okay, sir. Mohan?
Okay. So, Dr. Reddy. Hello.
Yes, sir. Tell me, sir.
So, if there is no question, then I like to close this lecture, and then I'll take a 5 minutes break. And next lecture is going to be a long 2-hour lecture. Basically, it will split between the first of my lecture, followed by a whole phase evolution sequence demonstration by my group member. Okay. So you can take a few minutes of break. And
by 11 o'clock again we will rejoin, sir.
Yeah, 11 o'clock, sharp 11 o'clock.
Sharp 11 o'clock we will join. So
okay. Yeah.
So I request all the participants to take break for 10 minutes exactly by 11 o'clock. Again, you can rejoin the session. Thank you.